I want to welcome you to the final day of the RIC. I know we've all had an opportunity to hear a lot of great presentations, so I hope you all have enjoyed those presentations and discussions and found them to be very, very rewarding. And so in keeping with that, I want to let you all know that we have saved the best for last. So thank you all for joining us today and my distinguished panelists, which I will introduce shortly. Again, or as you all are aware, the session title is Exploring Opportunities for the Safe and Economic Design and Construction of New and Advanced Reactors. And before I introduce our five panelists, I'm going to quickly run through some of the housekeeping items that you've heard throughout the week, so bear with me. So very quickly, you'll see the QR code here behind me. We're going to use that for the Q&A session. So make sure to scan that. You'll see options for questions, how you want to send those forward. It could be for any one of our panelists. It doesn't clearly articulate if you want a question that goes to all of the panelists. So if you do have something you'd like a response from all five, just leave the name blank, and then we'll have the session coordinators make sure that that's flagged for my asking. We will hold all questions until the end, so we'll have the round of presentations. We'll hear from everybody here, and then we'll do the typical Q&A afterwards. And one last one before I continue going on is just making sure that people are silencing their cell phones at this point. Okay, so let me turn to our five panelists in the order that they will be presenting. First, I want to welcome Dr. Junya Sumita. Dr. Junya Sumita is a senior principal researcher at the Japan Atomic Energy Agency, where he has worked since 1998. He is currently working in the High Temperature Gas-Cooled Reactor Project Management Office. Dr. Sumita earned a Doctor of Engineering degree with an emphasis on graphite materials. He spent over 8 years within the High Temperature Engineering Test Reactor operation and maintenance section working at the High Temperature Engineering Test Reactor projects. Next, I want to welcome Emma Redfoot. Emma Redfoot is the Siting and Environmental Lead at Oklo, where she specializes in the licensing and policy aspects related to the safety and environmental regulations governing the siting of nuclear facilities. Ms. Redfoot holds a bachelor's in environmental studies and a master's in nuclear engineering. She has been with Oklo since 2018, bringing expertise in navigating the regulatory landscape for siting of advanced nuclear facilities. To her left, we have Dr. John Stamatakos, and he is a geologist and geophysicist who holds a PhD from Lehigh University. He is currently an institute scientist at Southwest Research Institute in San Antonio, Texas, which he joined in 1995. At SWRI, Dr. Stamatakos has performed basic and applied research on natural phenomena hazards, mainly related to probabilistic seismic hazard analysis. This work has included seismic hazard studies for numerous commercial nuclear facilities in the U.S. and abroad, mainly in support of the U.S. Nuclear Regulatory Commission. And to his left, we have John Richards. John is a senior technical executive in the Risk and Safety Management Program of the nuclear power sector at the Electric Power Research Institute. His research activities focus on the development and the application. Bear with me as I realize I haven't moved the slides. There we go. Focus on the development and application of methods and tools for the seismic evaluation of nuclear power plant structures, systems, and components. John joined EPRI in 2012 and leads EPRI's seismic risk research, focusing primarily on seismic probabilistic risk assessment methods and applications of seismic risk insights. Prior to joining EPRI, John worked for 30 years at Duke Energy, where he performed and managed all aspects of seismic qualification activities at Duke Energy's nuclear power plants. And our last but not least speaker, Dr. Andrew Whitaker. Dr. Whitaker is a SUNY Distinguished Professor in the Department of Civil, Structural, and Environmental Engineering at the University of Buffalo and holds a faculty joint appointment at the Idaho National Laboratory. Dr. Whitaker is a registered civil and structural engineer in the state of California. His undergraduate degree in civil engineering is from the University of Melbourne, and his master's and PhD degrees are from the University of California, Berkeley. Dr. Whitaker has served the U.S. nuclear industry for 20 plus years in a range of capacities. Okay, and just turning to the session, in today's session, we are going to keep with the theme of new and advanced reactors, as we've heard through the various sessions all week. The safe and economic design and construction of nuclear power plant structures that will withstand seismic events is a critical area of investigation to support new and advanced reactor designs. These advanced designs that range from microreactors to plants that will produce hundreds of megawatts in electricity encourage the use of tailored approaches, such as risk-informed, performance-based efforts, to analyzing seismic hazard and other demands, rather than applying a one-size-fits-all approach to accounting for varying risk and consequences. So, in that end, our panelists, comprised of leading experts from industry and research institutions and proponents of new and advanced reactor designs, will present their perspectives, which will include the use of risk-informed, performance-based design approaches, tailored approaches for seismic hazard characterization, and perspectives on the feasibility of applying commercial building construction codes, and the potential application of protective systems such as seismic isolation. And with that, I will turn it over to our first speaker, Dr. Junya Sumida.
Okay, so thank you, Chairman. So I am Junya Sumida, working for JAEA, Japan Atomic Energy Research, Japan Atomic Energy Agency. So I'm very honored to be here, and thank you for giving me the opportunity to make presentation. Okay, so I'm going to talk about seismic design and licensing experiments of HTTR. So HTTR, high temperature engineering test reactor in Japan. HTTR is the only prismatic type high temperature gas cooled reactor in operation in the world. So major specifications of the HTTR are shown here. Its thermal power of 30 megawatt and coated fuel particle graphite helium are used for fuel core material and coolant. And inlet temperature of helium coolant is 350 degrees C, and outlet temperature of the helium coolant is 950 degrees C. The pressure of the helium coolant is 4 megapascal. And HTTR was attained its first criticality in November 1998, following the full powered operation in December 2001. And the restart operation of HTTR is attained so in July 2021, and the station blackout test and LOFC, loss of host cooling test, at 100% reactor power. These were attained in January 2022 and also March 2024. Okay, so I'm going to talk about safety demonstration test and seismic design. So safety demonstration tests have been carried out to confirm inherent safety features of HTTR using the HTTR under OECD NEA framework. There are three types of tests. One is the LOC test at the power of 30%, and the station blackout test, also LOFC test at the power of 100%. So I'd like to show one of the results of our safety demonstration test. So this figure shows the result of LOFC test at 100 reactor power. So the reactor intrinsically shut down as soon as the core cooling flow rate approaches zero, and the reactor is kept stable long after the loss of core cooling. So we successfully demonstrated that the safety of the HTGR. And also, these safety demonstration test data are useful for safety evaluation of HTGR in future. And this diagram shows the methodology for seismic analysis of HTTR. Firstly, so we survey site ground and active fault in HTTR site, and we prepared design basis seismic ground motion and seismic spectra, and also we prepared fluor response spectra. And finally, we carried out seismic analysis. So in seismic analysis, so we have developed the SONACHINA, we call SONACHINA 2V code, to analyze the behavior of the HTTR core graphite components under the seismic excitation. So this code used to predict the impact phenomena between graphite blocks and to provide information on impact forces, displacements, and so on. Okay, so this slide shows one of the results of the seismic analysis. So time history response of reactor building was conducted to generate the input data to next analysis, and time history response of reactor pressure vessel was conducted, and then so core structure was modeled, shown as this figure, and performed the analysis using the SONACHINA code in order to calculate displacement, impact forces, and so on. And after that, so using using these data, so FEM analysis was calculated to obtain the stress of the components. And this table gives the stress of the components of RPV and support post. As we can see this figure, this table, that also the obtained stress were less than the limit of the stress. Next, I'm going to talk about the conformity to new regulatory requirements. So after the Fukushima Daiichi nuclear power station accident, so revised regulatory requirements were issued by the NRA in Japan, and JAEA submitted the application, including evaluation results satisfying the new regulatory requirement to NRA. And through many discussions with NRA, so JAEA obtained the permission by the NRA, and HTTR restarted its operation on July 30, 2021. So this table gives the result of safety review of Nuclear Regulation Authority. So the left-hand column shows the major discussion items on reviewing by NRA. So, for example, so the evaluation, for example, regarding the earthquake, the evaluation of seismic design classification was discussed. The sum of safety system structures and components were classified from S class to B class based on the result of safety demonstration test. For example, so core heat removal system, which is classified originally S class, so we are discussing its changes to B class. Also, so reactor internal structures originally S classes, classified S class, we discussed it changed to B class. And the regulatory review results are shown that so no large-scale reinforcement due to the degradation of the SSCs, so additional countermeasures are not required for the earthquake. So JAEA has many experience on safety licensing and lots of data needed for HTDR safety licensing. Okay, so I'll talk about the downgrade of safety and seismic classifications. So this left-hand column shows fundamental safety functions For example, as for control of reactivity, originally safety design required controlled system and reserve shutdown system. On the other hand, after LOSC test, by using the LOSC test result, so it is negative temperature coefficient of reactivity is considered as new safety design. And also for removal of heat from the core, heat removal from the core by natural phenomena and core coolable geometry is not important in accident conditions. These concepts are available for new safety design. Also for confinement of radioactive material, confinement by triso-coated fluid particles, this concept is available for new safety design. And based on these results, so downgrade of classification of the SSC was approved by NRA. So SSC means reactor shutdown system, vessel cooling system, emergency application system, which are shown in the bottom of the left hand. Okay, so I'm going to talk about development of demonstration reactor in Japan. So Japanese government put forward development and construction of next generation advanced reactors that incorporated new safety mechanism on the premise of reactor safety, and this table gives the schedule of the development of the demonstration reactor in Japan. So demonstration reactor of HTGR scheduled to start its operation later 2030. Okay, so in order to realize HTGR commercialization, there are some challenges and approaches. So for challenge of policies, so we need project predictability, and also for society, we need to select the site and develop the business scheme. And also, so for technology, we need to develop the reactor technologies, such as reactor core components, which need to scale up, and also fuel and code under standards. And also, we need to develop heat application technologies, such as coupling system and hydrogen production systems. So throughout these challenges, approaches will be solved throughout the HTGR demonstration reactor development and HTTR heat application test. Okay, so this slide shows the HTGR demonstration reactor development in Japan. So reactor power will be range from 150 megawatt to 250 megawatt, and supply very high temperature above 800 degrees C to hydrogen plant, and waste heat can be used for power generation to be supplied to internal load of steel making plant. And combination with the carbon-free hydrogen production technology enables large-scale, low-cost carbon-free hydrogen. And this table gives the candidation method to produce the hydrogen. So as you know, steam methane reforming system produce the carbon dioxide, but other three systems do not produce hydrogen. Does not produce the carbon dioxide through producing the hydrogen. So one of Japanese maker is now carrying out the feasibility study to survey so which method is useful for HTGR in future. And finally, I'd like to show our test HTGR heat application test. So hydrogen plant will be located next to the HTGR building to establish the design for the coupling of HTDR and hydrogen plant, and to demonstrate the performance of components required for this coupling. For example, high temperature isolation valves, hot gas duct, and so on, using the HTTR. So this table shows the schedule of the HTTR heat application test. Now we are about to apply the licensing to NRA by the end of this month, and design of HTTR modification and design of hydrogen plant has been carried out, and following to modification of HTTR and also manufacturing and installation of the system into the HTTR in order to produce the hydrogen in 2028. Okay, this is a summary of my presentation, but I'll skip this slide. Thank you very much.
All right, thank you so much, Dr. Junya. So we're going to hold a round of applause until the end, and with that, we're going to keep us going, and we'll hear now from Emma Redfoot.
Can you skip? Okay. Skip.
Oh.
Skip.
Okay. Thank you so much for inviting me to join this panel and to have this discussion. I think this is an incredibly important topic, and I'm really excited to be here. I'm hoping to present in this presentation to give a sense of why what we're talking about is so important to allow for deployment of the amount of clean energy that we need to meet our energy goals and the massive amount of demand that we have right now. So today I'm going to talk a little bit about an introduction to the company and just a brief discussion of the technology. Then I'm going to talk about the regulations that drive both like seismic design and site characterization. As the siting lead for Oklo, site characterization is more my focus, but seismic design and characterization are inherently linked because of needing to risk inform site characterization. So I'll have a little bit of a discussion of that and on the precedent around what kind of seismic design and site characterization has been performed for low-risk facilities, such as research and test reactors and the DOE facilities. I'll then finally quickly summarize what we are proposing in terms of what is the appropriate path forward for site characterization for these lower risk advanced reactors. So Oklo is a startup, it's an advanced reactor startup, and our mission is to provide clean, reliable, and affordable energy on a global scale. That's important for this presentation because to emphasize that we're talking about a global scale, we're talking about a lot of deployment. And we're clearly seeing a time when there's even more demand than ever before. We focus on fast reactors, and that includes being able to recycle our fuel. So not only are our deployment of these kind of reactors allowing for the massive amount of energy that we need, but it also mitigates the waste burden for the country. So doing this quickly is really important. So brief overview of the technology. This is the Aurora Powerhouse, so it's the Aurora product line. These are inherently safe and simple designs and to allow for rapid deployment. Rapid deployment and mass deployment is a part of all of the design considerations we have built in, including consideration of seismic impacts and site characterization. And so by having that demonstrably low consequence design, that really invites a reevaluation of what is the appropriate site characterization, given the assumption is no longer, hey, if something fails, a lot of people are going to get hurt. So the technology is based on experimental breeder reactor 2. So this is going in line with our overall philosophy of rapid deployment. Experimental breeder reactor 2 operated for 30 years at Idaho National Laboratory. It demonstrated some incredible inherent safety properties that forms the basis of the Aurora design that we can leverage. So using a mature technology to support our reactor design supports our overall efforts to rapidly deploy. Okay, so I'm going to have a brief regulatory overview. So a lot of the times when I think about seismic, it's really broken into the structural aspect and the site characterization aspect. The regulations are written that in a way that's trying to say you should consider performance, you should consider what is adequate engineering solutions for determining for your site characterization. But the way that it's treated, because these are two different specialties, ends up, the discussions are often a little bit separate about, did you characterize the site sufficiently? How are you designing the reactor for appropriate structural loads, when really they need to be linked. So right now, the way that these regulations are addressed, you identify the safe shutdown earthquake as required in Appendix S to Part 50. That is the ground motion that you need to show your safety functions for generally your safety-related structure systems and components are going to maintain that safety function. As part of that definition of the safe shutdown earthquake, it includes what's at the bottom of this slide, which is 5034. That is the consequence that is kind of emphasized as being relevant. And so this is a regulation that is looking at performance-based in that aspect, but it's not been used for commercial nuclear facilities commercial nuclear power plants that are significantly lower risk. And then 10 CFR Part 100.23 requires the site characterization, including uncertainty. And generally, these are the guidance, that Reg Guide 1.29, in terms of identifying what are the SSEs that you need to consider for the SSE. Reg Guide 1.208 is how you do the PSHA, the probabilistic seismic hazards analysis. And then ASC 43 and ASC 4 are standards that support doing that seismic design. ANS 2.27 and 2.29 are used for more non-commercial facilities. So the big question is, how are we incorporating inherent safety and robustness in the design so that we can address site characterization, which is something that has to happen very early on in a project. And so in order to get to licensing, you have to do this. So this is a barrier to entry that if we can right-size it, can make a huge difference in terms of deployment. The guidance that discusses how do you actually perform a consequence analysis, ANS 2.26, and then a DOE standard and a DOE handbook that discuss, because the DOE works with something other than commercial nuclear power plants, how do you look at a low consequence facility, or how do you look at a facility that the assumption isn't that it's high consequence. And so these are the kind of precedent that we're looking at to to perform our consequence analysis, and then that relates to what is the appropriate site characterization. So getting to kind of how is this, like the risk-informed aspect of it is, okay, so given your consequence is low, you show that, then how should that change your site characterization? If you have seismic design category 1 and 2, which is defined based on what is the impact to workers, the public, and the environment, if you can show that that is a low impact, then what is the appropriate performance metric is more in line with what is considered in building code. And building code is incredibly robust. It's used for very hazardous facilities and been shown time and time again to be sufficient. Right now, the assumption is that nuclear power plants are SDC 5, and you can see the recurrence interval there for what you evaluate every 10,000 years is much higher, and that's a lot more time and money spent up front on a project to characterize a site up to a point that may not be appropriate given the consequence of the facility. So I'm going to try to quickly run through the methodology here so that I'm not using up too much time. So reiterating what is important to us: rapid deployment, safety, and affordability. This approach, doing a demonstration that you're low consequences, really showing that you're safe, pushing for right-sizing site characterization, really incentivizes having that kind of safety because there's a big benefit there. And then rapid deployment. If you are able to show your low consequence and use building code, not only is that like an incredible resource that has been used time and time again, but it unlocks a whole new workforce of people who work with building code all the time. So this is a brief summary of how you perform that consequence analysis. It's really looking at failure of specific structure, systems, and components that are relevant to safety, while accounting for system interaction, defense in depth, redundancy, common cause failure, and robustness after first assuming basically everything fails. So that's based on established guidance by ANS and DOE. And then once that's complete, and you've identified what is your seismic design category, that is when you go back and say, okay, what is the appropriate site characterization, the appropriate recurrence interval to design for based on that consequence analysis. And if you can show your low consequence, the appropriate tool for site characterization is building code, and that is something that is pointed to in guidance like ANS 2.26. For us, we're also, for the rapid deployment, I will emphasize that we're not designing the reactor for each and every site differently. We're designing it to be sited in as many locations as possible. So a design response spectrum that is bounding, that's high. So even more margin is built in because of that for a very robust design. And this allows for rapid deployment, emphasizing the safety, and as well as mitigating those initial site characterization costs for a project. Okay, thanks so much. I know we're taking questions at the end here.
All right, thank you, Emma. And we will jump to our next presenter, Dr. Stamatakos.
Yeah, good morning. Good morning. So I'm going to quickly summarize the activities that we've been conducting, supporting these concepts we're talking about this morning in terms of changes in seismic design requirements, and I'm going to talk through a study that we just completed on how we might be able to do a simplified shack for some of these advanced reactors that don't need the full long scheduled shack study. So it'll be in two parts, and I'll try to go through those quickly, just emphasizing some of the information with highlighting how the details of that information are available and where you can find them. So the first part has to do with the work we're doing on the risk-informed and performance-based seismic design framework. This goes back to some work we started in 2020, 2021. We were tasked from the NRC to look at how we could incorporate the concepts from ASC 43 with the ideas of modifying the regulations. We were supporting the first version of 10 CFR Part 53 in this work, and so at that time we were just considering sort of the Chinese menu options of matching various levels of SDCs and limit states, and evaluating how that might play out together. So that study was first done, and we produced a research information letter in 2021 that walked through those with examples of how those could be implemented. The goal of that then was to support the development of some reg guides. So we've done that. This slide just highlights that initial work. So the cover page for the RIL is on the left. We produced a paper that was published in an essay in 2023 that also summarizes some of that basic information So that's where we started with this work. And since then, we've been working with NRC to develop a couple of draft reg guides in support of that. One is on the risk-informed performance-based design. Now we're in the second or third or fourth iteration, keeping up with the changes to Part 53. So that's now in the NRC review process, and a parallel one looking at base isolation, seismic base isolation. That's also in the throes of getting reviews and trying to be compatible with the latest version of Part 53. We're going to revise our 2021 RIL to turn that into the supporting tech-based new reg. The team that's working on this is I think, familiar to many people who are working in this area. I'm working with Neelish Choksi, who's here in the front row. He's our captain, he's our leader. We're in Bob Budnitz and Ravi Ravinda. And then at Southwest, Kristen Ulmer, Daniel Woodworth, working with Tom Houston on some of the, especially the ASC 7 questions. And I'm the cat herder of this group. We're also now, because it's, this is not something we thought of originally, but has really come into the fore, as you've just heard in the prior talk, how we can evaluate the application of industry building codes and standards and SSE classifications. And so there is some discussion of that in these reg guides. But obviously, I think as we're hearing this, there's a lot more work that needs to be done in that area. This is just an example flow chart of how we've laid out our options in this draft reg guide. We provide 3 basic options. Option 1 sort of follows a very traditional approach, a very traditional Part 50 approach. Options 2 and 3 are much more geared towards the LMP framework. In fact, option 2 very much follows the LMP model with the PRA sort of leading the way of identifying how you can right size and right design your SSCs to get a nice appropriate balance of those in getting a good risk profile for your facility. Option 3 has even more flexibility in the sense that there are other ways that you can evaluate the importance of risk up front in addition to the PRA that gets you then to the endpoint. I would point out in those draft reg guides, when they become available for you to look at, there's a couple of appendices that have simplified examples of how those could be applied. And we're hopeful that that'll be helpful when you get to finally see those in print. Okay. A little bit closer to my own heart is the study we did with NRC. We did a PSHA study to demonstrate how you might be able to do a SHAC Level 1 study to meet the requirements for some of the advanced reactors. For those of you not familiar with SHAC, it's a process that was developed starting in the late 1990s to evaluate differences in seismic hazard analyses that were done for existing nuclear power plants. There was a controversy because of differences between what Livermore had produced and what EPRI had produced in terms of the outcome. So there was a process that was developed to basically how you do a structured judgment or structured expert elicitation to get to an answer for a seismic hazard. SHAC has been used and applied many, many times all over the world. The SHAC comes in 4 flavors, increasing from 1 to 4 in terms of complexity and schedule and cost. So SHAC Level 1 is the most basic, simplest approach. And what we wanted to try to do was to see if we could put together a team, follow the process of SHAC, but do it at a Level 1 and try to do something that was 6 to 9 month schedule rather than a sort of 2-year schedule, which is typical for these very large SHAC studies. And come up with some notions of how to do that and make those savings. So evaluate contributions from existing SHAC studies. We obviously wanted to focus on annual exceedance frequencies less than 10 to the minus 4. That was an important part of that. And there are important differences that come out because of that. And some ways that we can simplify the process, make recommendations, focus on only those aspects that are most important in contributing to the hazard as a way of doing the study. So we picked the Skull Valley site as our demonstration site. Skull Valley site was the site proposed in the late 1990s for an interim storage facility on the Goshute Reservation in Utah. There was a seismic hazard study that was done by Geomatrix and published in 1999 and again 2000. So we picked the site because there was a lot of data, so we could evaluate sensitivity studies. We could test some of our ideas of how to do simplifications. It's a site that has both faults and a good background source zone, so there's a lot of information on seismicity. It's a pretty high seismic site. So we picked that site. There's a report that's out there that we have that justifies in much more detail why that site we thought was appropriate for this demonstration project. And I'm showing you the cover page of the Geomatrix report that was published in 1999 that supported a lot of that evaluation. But it wasn't just their data that we used. We used a lot of USGS information, and I'll talk about that as well. So out of that, we produced 2 documents. These will be 2 research information letters that will also hopefully be published quite soon. One of them is the SHAC study itself, so it provides sort of a format and content, if you will, guide for future SHAC 1 studies, and I think it's a pretty complete document. I'm actually quite proud of the team and what we were able to produce there. But we also produced a companion recommendations report that has a lot of interesting information, I think, that of things that we discovered along the way and some advances that I think will really help process in the future. The technical team I was the lead of the SHAC, but I worked with Cliff Munson and Tom Weaver at NRC, Kristen Ulmer at Southwest Research, Ryan Payne here at NRC, Adrian Regis-Merrick, who's a professor at Virginia Tech. Our participatory peer review panel was John Ake and Gabe Toro. So that was the background of that study. I won't talk about the results in great detail, but I just felt obligated to have a slide that had results. So you see the seismic hazard curves on the left and the uniform hazard response spectrum and the GMRS in the center, and then the tornado plot, which shows what we now know at almost all SHAC studies is that the thing that really controls the uncertainty in seismic hazard analysis is site response and the site term. That's the most important, and I think going forward, being able to reduce that uncertainty, I think will have the greatest benefit in reducing overall uncertainty in all of these seismic hazard studies. One of the things that was interesting, kind of a little unexpected to us as an outcome when we started to pull the SHAC apart and look at what was contributing to the hazard comparison here is what contributes to the hazard at 10 to the minus 4 compared to the 10 to the minus 3. One of the things that comes out of this is that at 10 to the minus 4, the long, big controlling faults really control the hazard. But when you're at 10 to the minus 3, other faults, especially local faults, can start to contribute. So there's not necessarily a blanket simplification in terms of when you get to a higher annual exceedance frequency, what happens in terms of what's controlling. We can show comparison of what we have with USGS at this site, and there's two curves. Our result actually is relatively close to what was in 2008, USGS 2018, but not at all close to anything from USGS 2024. USGS 2024 has a much different source model. One of the things we discovered in this analysis with using USGS data is that, the USGS has this huge mission, and it's impossible for them, I think, to keep up with all of the information that's out there and is available. We discovered that depending on which sources we were looking at, there were differences in their interpretations of fault lengths, fault rate activities. Their quaternary database has different interpretations of the fault activities than are used in their latest seismic hazard model. Their latest seismic hazard model uses a lot of GPS data for their rates, which is not something that's been done in many other studies. So there are very important differences, I think, in how those are applied, because USGS has a different mission than trying to really understand and characterize the seismic hazard at your site. Here's the comparison of the deaggregation for the SHAC, our SHAC study, and the USGS. And again, because of the way that the USGS has quantified their fault sources, they don't, the contributions of those faults to their hazard compared to what we had from our study are different. And I think it's important to recognize that, that there are simplifications, especially in the USGS hazard model, that they need to make because of what their mission is, that you would miss if you hadn't dug in at least at some level and understood the details of the geology and the seismology at your site. A couple of other interesting and I think positive outcomes of the work that we did. We developed a new generic ground motion model for the Western United States. What's shown on that left figure is a comparison of those with the ground motion models that were developed for other shack studies, recent shack studies at INL and Hanford and others. The uncertainty is a little larger in our model, but it is a model that can be applied now, I think, across the Western United States, and that's documented in that report. The other thing we did is because we embedded our hazard analysts with our team in doing hazard calculations throughout the process, we were able to really find ways to simplify logic trees in ways that affect the outcome. So on the right, we're just showing a comparison of a portion of a logic tree for a fault source where we looked at the full logic tree with 18 or 20,000, I can't read the number from here, but a large number of runs through the hazard curve. And then the trimmed one, and what we show is basically we can recapture all of the fractals with our trimmed logic tree as we could with the full logic tree, saving a lot of computation time and analysis time. So in summary, I quickly discussed some of the work we're doing in the enhanced risk-informed performance-based design methodologies and the documentation of that will hopefully be out very soon, that will become available for everybody to review and provide feedback on. The demonstration shack project was completed. We think we did that within a reasonable schedule and a cost commensurate with the risk profile of some of these advanced reactors. I will say that personally, not speaking for the NRC, I do agree that at some point even that is too much. That for really low risk facilities, there should probably be other alternatives. But the approach that we have here meets all of the requirements of 1.208 and meets the requirements in 10 CFR Part 100.23. And in producing that shack study, we showed the benefits of having to do a dedicated and an analysis for site-specific study in order to make sure that you capture everything that's important and contributing to the seismic hazard at your site. So with that, I will pass on and take questions at the end.
Oh, thank you so much, John. And next, we'll turn to John Richards.
Good morning. I opted to stand up so Chris wasn't the only one to use this microphone here. I feel like a little bit of a Monty Python moment, and now I'm for something completely different. I'm going to talk a little bit about some research that we have done at EPRI on using risk-informed design for advanced reactors and how to account for the seismic risk in the design. Just a very quick overview of that, and then at the end a slide on some risk that research that we're still doing, that we're just getting into. So in this case, the work that we have done over the last year or two, we started with a very simple event tree that would be used in a seismic PRA. This is the way the PRA sees the plant. And if you're a risk person, you can check out for a couple of minutes while I explain that. But there's in the first column of this diagram is the seismic event, and there's a probability for that. And the next column in this one is reactor building failure, which in this case was a displacement larger than we wanted. There's a probability assigned to that happening based on all the analysis that goes into it. If you go down on that tree, it's assumed to fail, and you end up with a frequency of assumed core melt at that point. If it goes up, it succeeds, and you have to move on through the rest of the tree. That's the way this tree works. So the second step was a failure assessment for the reactor vessel and the supports. The third step was a failure of a Scram function. And then the last two steps were different cooling, backup cooling. There's a primary coolant, a primary cooling system, and a backup cooling system. And you go through all these with this up and down step to assume if they succeed or don't. When you get to the very end, you have the very top two items don't result in core melt because you have enough successes combined that you prevent that. But any of the other branches have some probability of happening that's calculated through this tree. So when you're considering a seismic event in this analysis, you end up doing fragility calculations for each of the elements that feed into this. And at the beginning of a design for, say, an advanced reactor, you might not have all those details, but you can assume allowables within the various standards, and you can assume that you're just meeting those allowables, and you can estimate a fragility off of that as you work your way through the process. So that all takes you to what's called a frequency consequence chart that happens in NEI 1804, which is the Licensing Modernization Project, and is a different concept for figuring out what's important in your design, what is safety related, what is beyond design basis, type of things. And this happens one event sequence at a time, one run through that event tree. And so what I have, what this diagram shows on the vertical axis is the frequency of the event happening. And on a horizontal axis is an estimate of the dose at the site boundary. The diagonal line that runs through that, or mostly diagonal line, is a goal, a target of what you're supposed to be aiming to achieve. Okay? Now, for one event that runs through the middle of this, I'm showing on this diagram a square box, which is the best estimate of that. And then there's a distribution up and down, which is the 5th and 95th percentile of how likely that event is to happen. And a horizontal distribution, 5th and 95th percentile of the release that would happen. So you're accounting for your best estimate as well as your uncertainties around that. And so every one of the endpoints in this event end up on this diagram. So the top two are the green ones, and they show up all the way on the left axis because those are success paths, so there's no release. The rest of them all go in different places as you work your way down, okay? There's a few hard spots on this diagram, and the red line that's shown down here is a release boundary constraint out of one of the laws. And so it's showing that one of these endpoints has a 95th percentile possibility of exceeding that. So that's an unacceptable endpoint. A few of the others are close to or above the diagonal line. Those would be undesired. You're above your goals. So in a risk-informed design, what would happen is you would go in and adjust your design. This is an iterative kind of process that happens in parallel, where you're studying your normal design characteristics and then your risk results out of that design, and they both kind of iterate together, which is a new way of thinking about how we do risk analysis. For the operating fleet, the designs were already done, and then we did an analysis, a risk analysis of the existing plant. In this process, one of the challenges is that you would need to iterate on the design and on the risk at the same time. So the design people need to understand a little bit about what the risk guys are analyzing and how it's influencing the results, and vice versa. The risk people need to understand what options the design people have in making some changes. So anyway, you can iterate through this process. For example, the red box at the very bottom is above the release that we would like to have. And so one simple answer would be that you would improve the seismic design of the reactor building in this particular case. Because what that is the very first branch in the event tree, the reactor building fails, and it's happening and providing a consequence beyond what we want. When you do that, if you follow the event tree, you're less likely to get to that first step and go down, which is good. That helps for the reactor building failure, but you're more likely to go, therefore, take the path up. So all those other likelihoods change as you work your way through. So this iterates through the process, but it can definitely be achieved, and it can be achieved in a way that produces a more cost-effective design all the way through. One of the interesting aspects that we're doing some work on now is that within the primary civil design standards, they already have a graded design process, a graded implementation process. This was put in place a long time ago, and that applies both for ASCE 7, which is a non-nuclear standard, and ASCE 43, which is the nuclear standard. And if the key parameter, the key result that you need out of your structural design anyway is to achieve a certain performance goal, that's achievable actually in either of these standards. So this is my last slide, and I just want to make the point. Looking at this slide, we did a very admittedly simplified look at the graded process available both in ASCE 43, which is the orange bars on the left, and ASCE 7, which are the blue bars on the right. And you can achieve different performance goals within the parameters of those standards. And so if that is the key result that you care about, it seems that you could likely achieve that even with just using commercial standards. Now, there's some devil in the details here, and we have not completed this research, but that's a path that we're pursuing, and we hope to be completing at least a good part of that research and publishing some of those results later this year. All right. So that's a different view of risk-informed design. Thank you.
Thank you, John. And then we will conclude with our last presenter, Dr. Andrew Whitaker.
Well, good morning. And I'm standing here so I can actually see the screen, which I couldn't see from the other end of the table. Anyway, well, my name's Andrew Whitaker, and I'm pleased to be here this morning. I thank the NRC for the invitation, and with luck, the slides are queued up. So you're going to accuse me later on of colluding with John Richards on a presentation, and I very much enjoy working with John, but we didn't collude this time round. So I'm going to talk about codes and standards for civil structures and why they might be appropriate for next generation nuclear. So as we look to update our nuclear codes and standards, we recognise that the world has changed, and we're no longer dealing with, in energy space, large light water reactors. So as we take our standards forward, we need to address large light water reactors, advanced reactors, micro reactors, reactors built to support industry and industry only, generating process heat, and by loose extension, marine reactors. So as we write the update of ASCE 4 and ASCE 43, which John Richards mentioned, we're affectionately calling that ASCE 92 in honour of the element uranium. We need to pay attention to our mission and our target audience. So right-sizing codes and standards. What do we mean here? Well, in my opinion, and in the opinion of my co-author Brian McDonald, our codes and standards must support innovation, and they can't stifle innovation. And non-nuclear structures, they are numerous. I've listed some of them here, starting with ASCE 722 that John Richards mentioned, ASCE 41, which is a standard for performance-based seismic design that I'll talk a little about later on, ASCE 59, which deals with blast loadings, ACI 318, and the AISC standards 360 and 341. So why use them? To Emma's point, to the point of John Richards, they've been used over and over and over again. They have stood the test of time. So they are widely used standards, and they address really everything that me as a civil structural engineer looking at nuclear would want them to address, namely analysis, performance-based design, detailing and construction, and also important topics like peer review and quality requirements. They are addressed explicitly in these standards. Have they served us well? Answer is yes. Have buildings collapsed when these codes and standards have been followed? No. So, as we look to next generation nuclear standards, what are they going to offer? ASCE 92, which is the merger of 4 and 43, that will address risk-informed, performance-based design explicitly. And we're going to point to non-nuclear codes and standards wherever we can, because those standards, again, have been used by industry and they've been used now for many decades. I'll make 2 points about the ACI and AISC standards, the nuclear standards. Namely, they address only limit state D, which is essentially elastic response, so you can't get to limit states A, B and C through these nuclear standards. And most importantly, these two nuclear standards point back to their non-nuclear counterparts for most of the provisions, so they are dependent documents. So let me just introduce these standards. John introduced ASCE 7. There's a series of statements here that cover what ASCE 7 addresses, everything from greenhouses with no humans inside to mission critical infrastructure, including hospitals. They address all loadings from gravity through seismic through lateral earth pressure. As John indicated, you can achieve elastic response with ASCE 7, which is maps to limit state D. You can achieve incipient collapse, which maps to limit state A, and everywhere in between. The ASCE 7 adopts as a basis the USGS seismic hazard tool that I think John Stamatakos identified a little earlier. There is design given what we call maximum considered earthquake shaking to indirectly achieve a risk target for limit state A. Nonlinear dynamic analysis is addressed explicitly, and I will add that it is now routine in the non-nuclear sectors, and it's been routine for about 20 years. Source structure interaction, which some, perhaps me, would say is a nuclear cottage industry, is used almost never, even for mission critical structures. And I think we need to revisit when that needs to be used and when it can be set aside for nuclear facilities. And the standard also addresses non-structural components and non-building structures. For one of the material standards, ACI 318, which is the code that ACI 349 depends on, it covers a wide range of topics on reinforced concrete structures, starting with loads and load combinations, moving through reinforcement details and construction documents and inspections. So we have standard process and procedure for evaluating materials, concrete and reinforcement, and then it gets into important topics such as checking of materials that are delivered to sites, inspection requirements, and so on. And importantly, the standard also has a section on design verification using nonlinear dynamic analysis, which you need to get to limit states A, B, and C. Moving on to risk-informed performance-based design. That's a hot topic in nuclear space. I'm pleased to report that in non-nuclear space we've been doing this since 1992. So the document on the left was a document we started work on in 1992 that deals with the seismic rehabilitation of buildings. Don't get too obsessed about the word rehabilitation. This document deals with the assessment of buildings that range in age from archaic, i.e. built in the late 1890s, all the way through to buildings with framing systems that comply with the most modern codes and standards. And these documents have developed over the course of the last 32 years, published most recently as ASCE 41, which is a standard for performance-based seismic design. Following on from the project that started in 1992, it was a project that started in the year 2000, and it added the risk component to the performance-based design. That resulted in a document that's known as FEMA P58 that's widely used in non-nuclear space. So we have gotten there in terms of risk-informed performance-based design, and there are a large number of design professionals that know how to implement this. So as I reconnect the dots, performance-based design for non-nuclear and nuclear. If I look at the nuclear standards, ASCE 43, that deals with performance-based design of nuclear structures. If I look at non-nuclear space, we have ASCE 41, which is performance-based design of civil structures, I'll call them. And the limit states that we have in ASCE 43 map to limit states or performance levels. We have an ASCE 41. So it's not surprising, because the same folks that were involved in the writing of ASCE 43 in the early days, including Robert Kennedy and Alan Cornell, were involved in the writing of the standards that started with FEMA 273 in the mid-1990s. So we can map nuclear to non-nuclear and non-nuclear to nuclear very, very easily. So as I look at high-performance structures and materials, there's a lot of information on this slide, but I just wanted to make one important point here with respect to concrete. The material itself is not that important. There are processes and procedures we have in our building code, ACI 318, that ensure the concrete strength or material strength is always going to be greater than the minimum specified. The real issue with structures is detailing. If I'm looking at a reinforced concrete structure, a key to success or a key to quality, key to performance is the detailing and the on-site construction inspection, which is standard fare in non-nuclear construction. And Fred Grant from SGH provided these images used at a meeting late last year. Both represent beam to column connections in what I'll call a special moment resisting frame. And the one on the left was designed by someone I will not identify. The one on the right was designed and detailed by a member of our National Academy of Engineering. And I think, as I say here, take your pick. I prefer the one on the right. But the one on the right is a result of having an experienced consultant and an excellent peer review team. This ensures that the design is of high quality. And that's absolutely critical in delivering nuclear structures. So peer review is an important facet of non-nuclear structures, or the design and construction of non-nuclear structures. Its purpose and scope is identified here. Peer review panels in non-nuclear space would include all of the disciplines involved in delivering a high-performance structure, starting with the hazard analysts, geologists, geotechnical engineers, and structural engineers. So it's a multidisciplinary undertaking, recognising that you need all disciplines engaged in delivering high-performance structures. You cannot compartmentalise a process. You can't have the hazard folks developing a product and handing it off to the geotechnical engineers, then handing it off to the structural engineers. It has to be an integrated process, and this is standard fare in non-nuclear space. So as I look at high-performance structures, my perspective on what we need. So a question to ask is, how good is good enough? And this is probably the only presentation at the RIC that will involve Ferraris and Porsches. But the point here is that we deliver high-performance structures each and every day via ASCE 7, and we can do the same with ASCE 92. Why should we be paying attention to non-nuclear US civil standards? It is my opinion that they are more than sufficient for US nuclear facilities, and to the point John Richards made a little earlier. We have tens of thousands of examples every year of these standards being deployed. Peer review is critical for high-performance civil structures. Innovation in non-nuclear sectors often happens decades before innovation in nuclear space because there are many, many more applications. Performance-based design has been a routine since the 1990s. We're just starting to talk about it in nuclear space now. And getting back to the question of non-nuclear US civil standards, are they good enough? My answer is yes. Is there any evidence of poorly performing code-compliant buildings? None to my knowledge. If you look at failures, why have they occurred? It's been, by and large, associated with inadequate engineering, poor construction, which you would deal with through peer review and appropriate on-site inspection. So let me just finish. What I've presented today is, yes, some of my work, but importantly the work of many others, some of whom are listed here. A special shout out to Bob Kennedy and Alan Cornell, both from Stanford University, and it pains me as a Berkeley graduate to say that, but they laid the underpinnings of risk-informed performance-based design in non-nuclear space and in nuclear space. And I'll close by saying that the plan for ASCE 92 is to complete our work by the end of the year and go out for public comment early in 2026. That document will include an explicit pathway for risk-informed performance-based design where someone decides what their target performance goal is, someone decides what their limit state is, and we will have an explicit process backed up by the peer-reviewed literature to deliver that product. One of the other important changes to ASCE 92 will be the seismic isolation provisions. We are overhauling those to ensure that they too are risk-based. So we'll have an explicit risk-based approach to deliver seismic isolation systems. So with that, I'll close, and again, thank you, Christian, for the opportunity to speak today.
Yes, let's give our presenters a round of applause. Thank you all, and fantastic presentations. So now we will open it up to the Q&A session. And again, you see the QR code up there, so please, if you have a question, scan it in there, and then we have our session coordinators that will be making sure that those are passed along to me. So we are going to start with the first question, and this one is being directed to Dr. Junya Sumida. And so the question is, what is the enrichment of the fuel for the demonstration reactor, and who will supply it?
Okay, thank you for your question. So, to be honest, so the fuel enrichment of demonstration reactor of Japan has not decided yet. But basically, so the same enrichment, same fuel type of same type of fuel of HTTR will be used for demonstration reactor on initial stage of demonstration reactor. So that means the average enrichment of HTTR is enrichment of HTTR is 6% in average. That means the initial stage for demonstration reactor, so the enrichment of 6%. But after that, so we need to reduce the cost of the demonstration reactor. We need to deploy. We need to introduce the more higher enrichment reactor than that of HTTR. And the second question is who supplier the fuel? Mm-hmm. Okay, so for the HTTR, so Japanese company NFI supplied the fuel to HTTR, and for the demonstration reactor now. So we are in Japan. We are now discussing who will supply the fuel to the demonstration reactor. So we are discussing with government and our JAEA, and Japanese company is now discussing. That's all. Okay.
Thank you. All right, we'll move on to the next one. The next one is for Emma Redfoot. How is the effect of aging taken into consideration when considering the seismic criteria for SSEs?
I mean, it's the same way that you consider aging for any structure. Like you're gonna, basically for all of if this is around seismic design categorization, you assume that things are gonna fail to show that you're a low risk facility. So that's how you consider it up front in terms of consequence considerations. In terms of maintenance over the lifetime of the reactor, you're gonna follow the standard practice and make sure that you're maintaining things and checking to see if anything's losing strength. So, yeah.
Okay, and it looks like the questions are going right down the line. So, John Stamatikos, next one's for you. Is there consideration of expanding the draft guides for risk-informed, performance-based seismic design developed for Part 53 to other regulatory frameworks, especially since LMP is agnostic to Part 50, 52, or 53?
Wow, yeah. We had considered that early on, and that was part of our mission when we first started those, but OGC recommended that we keep those separate and we focus on Part 53. But I think that there are examples where sort of the LMP and the concepts that are embedded in those could certainly be used for Part 50 or Part 52. But the specific designation for these reg guides will be for 53.
Okay, thank you. All right, John Richards. Estimates suggest there are between 40 and 80 American companies working on advanced reactors, microreactors, and SMRs. How many of these companies are involved in your research project? Additionally, could you share any insights into their perspectives on the research you have conducted so far?
Okay, thanks for that very simple question. I would say that EPRI has, under nuclear, a section called Advanced Nuclear Technology, A&T, and there are many, many, many of the applicable companies that are members of that research. And so that would include many of the normal utilities, both domestic and international, but it would also include many of the plant designers, including, for example, Oklo. It would also include companies like Microsoft and Google, who are very interested in licensing sites. So they are all engaged. Many of them are engaged. Now, we meet twice a year with our members and discuss the research that's going on, so they receive all those presentations and have opportunities to advise us on the things that are important to them for us to be working on. So there's an awful lot of players, and as you can imagine, it's really moving quite quickly. It's sort of like drinking from a fire hose to try and keep up with all of the various interests and needs.
All right, thank you. All right, Andrew, I'm coming for you next. This one's a long one, so if you need me to repeat it, please let me know. How does your proposal regarding use of USGS ASCE PSHA tool meet the regulatory need for consistency over time and inclusion of hazard significant model elements when the national seismic hazard maps are known to have large differences between models at some sites and do not include many hazard significant elements, for example, local faults, ground motion, epistemic, uncertainty?
I'm assuming I've got 4 hours to answer this. As some of you know, there's strong opinions on process and procedure, and this is probably not the time to get into all of those details. There are differences, But two things I will point out, and that is that whomsoever makes the hazard calculations are guaranteed to be wrong. Guaranteed to be wrong. And the issue then becomes who's least wrong, and we'll never know. So it is important that we have a discussion going forward about SHAC versus USGS and when is USGS good enough. There are many experts involved in the development of the USGS seismic hazard maps. They have a series of opinions, and if you execute a PSHA, whether it's SHAC related or not, you're going to get a different answer, guaranteed, unless you use the same ground motion models, you use the same inputs, you'll get a different answer. So this is an issue that we need to unpack fairly quickly, but we need to understand that everyone's guaranteed to be wrong. And importantly, we need to involve geotechnical engineers and structural engineers, practicing engineers in these discussions, because they're the end users of these ground motion products, regardless of who develops them. In non-nuclear space, when you stand up a peer review panel for, let's say, some seismic hazard calculations, you'll always find a structural engineer, an end user, as part of that discussion, because she or he will say, this is important, this is not important. Focus on these three things and set aside three other things. So it's important as we carry this discussion forward that the end users, namely the structural engineers, the risk analysts, they're seated at the table. And perhaps they're not seated at the table at this point in time. But it is a really important discussion. I was talking with Dr. Weaver a little earlier about how we bring a group together in the not too distant future to try and figure out a good pathway forward. So, not a complete answer to your question, certainly none of the details, but again, that would take hours.
Yeah, no, but thank you for that. Absolutely.
So one of the differences, though, Andrew, that I think is really important to highlight is that all SHAC studies, it's not just focused on the right answer or what we think is the right answer that may be wrong, but it's the full capture of uncertainty, and that's not something that's represented in USGS models. So the focus, I think that the advantage that I would say Team SHAC has clearly is that we spend a lot of time making sure that we understand the aleatory variability and the epistemic uncertainty, and that those are incorporated so that you have an appreciation and risk space for what the uncertainty is of what you think the answer is. And that's not something that is inherent in the USGS doesn't have the time or the space or the calculation capabilities to do that.
I think we have the basis for 8 hours of discussion, not 4. So let's go on to the next.
Yeah, I'm going to keep us moving because I got another one coming right for you again, Andrew. So listening to your presentation and the focus on nuclear codes, what is the significance of ASCE 92, and how would that differ from non-nuclear codes and offer? Is it a range of limit states and performance?
So what we have in ASCE 7 now is a defined maximum considered earthquake. It's loosely attached to a hazard with a return period of 2,500 years, and we go from what we call MCE hazard to design basis hazard through a factor of 1.5, which has a rich history in work done by Alan Cornell in the late 1980s. But then there is a deterministic process that's followed. What we're going to lay out in ASCE 92 is a probabilistic basis or a fragility-based approach to go from a user-specified target performance goal to a design basis earthquake. And from the design basis earthquake, we're going to introduce what we call an assessment basis event at around 150% of design basis, and there's a theme here, and we then perform explicit analysis at that assessment level to demonstrate performance. So the essence of performance-based seismic design is that you develop a design and then you evaluate it and demonstrate by calculation conformance. So here we're going to step away a little from commercial practice by saying, you give me a target performance goal and I'll determine the hazard level. ASCE 7 says, here's the hazard level and this is the expected performance. So we're turning the process around. But many of the parts to the process will be the same as what we do routinely in commercial building space. So again, in ASCE 92, we're going to focus on what makes nuclear different, and frankly, it's not much.
Mm-hmm. Okay, thank you. And we will go now to Emma. Given that microreactors will likely be mass-produced and will operate most of the time while research reactors and DOE facilities tend to be one-of-a-kind and operate sporadically, and the DOE facilities are in remote, isolated locations, will this have an implication on the desirable safety level?
Yeah, thanks for the question. I think this is an interesting one. So the precedent, I'm guessing this is based on me mentioning that the precedent around how you determine seismic design categories based on other low-risk facilities, which have been largely research and test reactors and DOE facilities. DOE facilities are interesting also because there's less of the motivation that we have for mass deployment. DOE facilities are incredibly well characterized already. So there's less of a reason to push to actually do like a consequence analysis and evaluate what is the appropriate size of design and appropriate size of site characterization. So I think that's a difference for sure. But what the precedent is that's important is, and the guidance that's important, is that these are facilities that have dose consequences that are more, and consequences in general that are more in line with a lot of advanced reactors. So, you can't really compare, you have to consider the safety of the facility when evaluating site characterization. And the reality is these advanced reactors look more like research and test reactors than they do like large light water reactors. So that's where you can build off of the established precedent around consequence analysis.
Okay, thank you for that. All right, we're coming back to you, Andrew. Do you think the regulatory oversight may have to increase to ensure code compliance if there is a transition to non-nuclear codes and standards?
Perhaps you're better positioned to answer that than me. If we transition to non-nuclear codes and standards, we ought to recognise that the standards that are used at the moment are dependent on those standards that we'd pivot to. The standards that we'd pivot to are modern, and if I pick on, say, ACI 318-19, that'll be reissued it'll be reissued this year, so there'll be an ACI 318-2025. ACI 349, which was issued quite recently, points back to, I think it's ACI 318-14. That won't be reissued until 2030. So when we get to 2029, ACI 349 will point back to ACI 318-14, and ACI 318-25 will be in the process of being revised and updated. So I think it might actually be easier, not harder. And as the staff looks to contribute to codes and standards, nuclear and perhaps non-nuclear, based on the discussion yesterday, embedding staff in the non-nuclear committees might be a very worthwhile enterprise.
Yeah, thanks for that. And looks like we have time for one last one. And John, this is coming for you. Are there concerns that employing non-nuclear standards essentially reduces the safety margin requirements and other considerations? Or is the idea to merge non-nuclear with nuclear standards based on risk-informed evaluations?
Which John?
You.
Me? Oh. Can you read that again?
Yeah, absolutely. Are there concerns that employing non-nuclear standards essentially reduces the safety margin requirements and other considerations? Or is the idea to merge non-nuclear with nuclear standards based on risk-informed evaluations?
Well, I think the latter is true. We do think that, there has to be some way of merging them based on risk considerations. The difficulty, I think, arises in practice because of the very different ways that in the current framework 43 and ASC arrive at performance, how those are treated, we have a lot of familiarity with working with limit state D. We have a lot less familiarity when we're near failure. So I think that from my perspective, there just has to be a lot more analysis that's done to show how that merging can be done safely and effectively, that we're not missing something, and that, the ultimate goal of meeting the performance targets and maintaining safety are maintained.
Okay. Andrew, you look like the other John would like to weigh in?
I would just add very quickly that the safety needs to feed into the performance goal, and then you have to achieve that performance goal based on the standards that you're using. And if it's not from a risk perspective, using the diagrams that I showed, if you didn't achieve the performance target that you needed, you could simply add, as part of your design specification, some additional parameters. Perhaps you enforce a higher margin or something like that. So you can still achieve the performance targets that you need that are derived from your safety goals.
I actually think the process is pretty straightforward. And I work in nuclear space and non-nuclear space on performance-based seismic design. So I think the process is straightforward. We need to understand that those working in non-nuclear space understand risk and they understand performance, and they've been doing it for 30 years. There's a lot more experience in non-nuclear space now than there is in nuclear space. So the nuclear community's got a lot to learn from their counterparts in non-nuclear space, whether it buildings, oil and gas, but the sectors have a body of knowledge that I think needs to be embraced. And I see the process as pretty straightforward. Importantly, performance-based design, to get to John Richards' point, is that if you execute a design and then you assess the design and you don't meet your performance goals, perhaps measured in terms of inelastic actions or deformations for limit states A, B and C, you update the design, and that might be strengthen a member, add some transverse reinforcement to improve rotation capacity, stiffen some elements to reduce deformations. This is standard process and procedure. It's been standard process and procedure for 30 years. There's nothing new here. So you develop a design, you assess it, and if it doesn't meet your target in terms of performance, you revise it. It's straightforward.
Well, thank you for that, and we are over time, but I want to make sure we thank our panelists, so thank you for a fantastic discussion.